Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be doing a video called Bridging the Gap Between Circuit Analysis and Signals and Systems, where essentially we're going to start off with a circuit located here, and then we're going to write some equations which we learned in our circuit analysis courses, and then try and map those equations to the equations we've learned in our signal and systems courses. In general, the point of this video is to try and correlate signal analysis to signals and systems, because as engineers, we sometimes tend to take these courses during different semesters or even different years. And so sometimes we don't know or we can't correlate these two things together. Where in this example, I'm going to bridge that gap and correlate both these courses. Before we dive into the mission at hand of this video, I want to make a quick note that when I am solving different equations in this video, I'm going to be referencing other videos I've made in the past, and these reference videos are going to be posted on the top right hand side corner of this video. Okay, so in this example, the first thing we want to do is solve for this v out of t in the time domain. So if I were to write our task down here, I could say the first thing we want to do is solve for v out of t, right, in the time domain. Right, this is in the time domain. The second thing we want to do is, if we consider that v out of t is equated to this y of t, and vi of t is equated to this x of t, we want to find y of t given that x of t is a given input convolved with h of t, which is going to be the impulse response of this circuit. So that's the second task at hand. And then the third thing we want to do is, again, solve for this y of t using what we call the Eigenfunction Theorem, which says that y of t is equated to the sum of n, h of Sn, an e to the Sn t, where n existed all natural numbers, where this h of Sn is what we call the transfer function of my system. Where the fourth and last thing we want to do is draw some conclusions, specifically about which method is easier to solve for y of t, method 2 or method 3. So again, we want to see if method 2 is easier than method 3, or if method 3 is easier than method 2. And this conclusion will also allow us to see the pros and cons about convolution, the Eigenfunction Theorem, and lastly, it would allow us to introduce or see why we need something called the Laplace Transform. Okay, so I hope these 4 goals, which I have displayed on the screen, allow us to see the path we want to take in this video. So let's go ahead and dive into it by first solving for this v out of t in the time domain. Okay, so now let's go ahead and solve for this v out of t. And something I want to note is that this v out of t, I will sometimes exchange as y of t, and this vi, or this voltage input of t, I will sometimes exchange with x of t in this video, just so that there's no ambiguity. Okay, so now let's go ahead and use KVL, which we've done many times in the past. And we could solve the voltage across the circuit and say that this is minus VI of t plus R times I plus V out of t is equated to 0. If I go ahead and consider that the current across this capacitor here, I, is equated to I is equals to my capacitance times the change in my voltage output, V out of t over dt. I can substitute this I for this I here. So then this becomes minus Vi of t plus R times C dV out of t over dt plus V out of t is equated to 0. If I go ahead and multiply both sides by 1 over RC, so I get dV out of t over dt plus 1 over RC V out of t Let me go ahead and move this term to the right-hand side. So this is equated to 1 over RC VI of t. If we go ahead and let tau equate to RC, then this equation becomes dV out of t over dt plus 1 over tau V out of t is equated to 1 over tau VI of t. Let me go ahead and call this equation 1, where this equation, if you remember from differential equations, is a first order original differential equation. And just to be explicit and as a refresher, so we're all on the same page, we say that a standard template for a first order ODE is dyt over dt plus pt yt is equated to qt, where pt and qt are continuous functions of t. But in this specific case here, pt is equated to 1 over tau. In calculus, we said that the integrating factor is this I of t, which is equated to e to the integral pt dt, which is equated to e to the integral 1 over tau dt, which is equated to e to the t over tau. I hope this makes sense. And now what we do with this integrating factor is we multiply this here by our equation number 1. So this here goes into this equation here. So if I rewrite equation 1, I'm left with e t over tau dv out of t over dt plus 1 over tau e t over tau v out of t is equated to 1 over tau e t over tau vi of t. Since this is a video, you can always pause the video, but let me go ahead and scroll down so I give myself some more room. And now what I'm going to say is that this whole thing here, I can equate to the derivative in terms of t of my voltage output t e to the t over tau. And essentially the reason why I can do this is because, again, if I take this derivative of v out of t e to the t over tau, what do I get? Using the product rule, again, this is from calculus, I get that I leave one of the terms alone. So let me leave e t over tau alone. And then I take the derivative of my second term, v out of t over dt. And then I add this to, I leave this term, v out of t alone. And then I take the derivative of my second term, so e to the t over tau. So then that derivative is 1 over tau, e to the t over tau. As you can see, this term here is the same as this term here. And this term here is the same as this term here. As a result, I have proved then that this whole term here is simply the derivative over time of v out of t e to the t over tau. I hope this step makes sense. So let me go ahead and continue. So then what can I say? I can say then that d over dt times v out of t e to the t over tau is equated to this term here, which is 1 over tau e to the t over tau vi of t. Okay, so the next thing I want to do is integrate both these functions. So what I'm going to do is integrate and change the integration variable. So I'm going to get the integral from 0 to t. I leave the first term alone. So this is d over d lambda. Again, I need to change my integration variable t, right? So all these t's need to change because I'm integrating from 0 to t. So I'm going to use a dumb variable lambda because I'm already using this tau here, which is my time constant equated to R times C, or my resistance times my capacitance. So then now this becomes V out of lambda E to the lambda over tau. And there's a d lambda here, which is equated to the integral from 0 to t, 1 over tau e to the lambda over tau vi of lambda d lambda. And now what I can say is that this d lambda here cancels out with this d lambda here. And essentially now we're integrating. So this integration here is with respect to this v out lambda e to the lambda over tau. So that just gets pulled out. So my answer on the left-hand side is going to be v out of lambda e to the lambda over tau, where my limits of integration stay the same, 0 to t, is equated to, I can pull out this 1 over tau because it's just a constant. So 1 over tau. This is the integral from 0 to t, vi of lambda e to the lambda over tau d lambda. If I go ahead and distribute these limits, I get v out of t e to the t over tau minus v out of 0 e to the 0 over tau is equated to 1 over tau integral from 0 to t vi of lambda e to the lambda over tau d lambda. So as you can see, e to the 0 over tau is simply just 1. And if I go ahead and move this term to the right-hand side, I simply get v out of t e to the t over tau is equated to v out of 0 plus 1 over tau integral from 0 to t vi of lambda e to the lambda over tau d lambda. If I go ahead and multiply my entire equation by e to the minus t over tau, I simply get v out of t is equated to v out at 0 e to the minus t over tau plus e to the minus t over tau integral from 0 to t vi of lambda e to the lambda over tau d lambda. Let me go ahead and move this down just a tad bit here. As you can see, in terms of lambda, this function here is just a constant, so I can move it into my integral. And so I get v out of t is equated to v out of 0 e to the minus t over tau plus 1 over tau integral from 0 to t vi of lambda e to the minus t over tau times e to the lambda over tau d lambda. And so then lastly, v out of t is then equated to v out of 0 e to the minus t over tau plus 1 over tau integral from 0 to t vi of lambda. I'm going to go ahead and combine these two exponential equations. And I'm going to say that this is e to the minus t minus lambda over tau d lambda. Where remember again, this tau is equated to my resistance times my capacitance. And let me go ahead and call this equation number 2. All right, so this concludes our step number 1, or our goal number 1 for this video, where essentially we wanted to find v out of t in the time domain. And this equation is very important because if you've ever studied the step response of an RC circuit, embedded in this equation is the equation associated with the step response of the RC circuit. And in order to see the derivation of the step response of an RC circuit, I have posted a video which I made in the past called Step Response of an RC Circuit Clearly Explained in the top right hand side corner of this video. And just as a general teaser, the equation that we talked about is using what's called the 5 equation. So final, initial, final, exponential. All right, if you have any questions or concerns about how we derive this equation here, please leave them down in the comment section below and I'll be sure to get back to you. So let's go ahead and move on to step number 2 of this video. Okay, so step number 2, we're tasked with finding this y of t, which is equated to x of t convolved with h of t, where we know that our x of t is equated to this cosine t u of t. And just as a quick drawing here, this simply means that it is 0 all the way until 0, and then it shoots up to 1 because cosine of 0 is 1, and then it starts to rotate like this all the way until infinity. Okay, so we've talked about this h of t in the past, which is called the impulse response. But if you need a refresher, I made a video called Convolution Example Part 1, where I discuss specifically on what the impulse response of a system is. But just as a brief recap, remember that if I have a system where I have an input vi of t, again, remember this is the same as x of t, and I pass it through a system, specifically an LTI system or a linear time invariant system, where this is capital H, which is this RC low pass filter circuit, which we saw on my very first slide. Then we say that V out of t, which is again equated to this y of t, is equated to my impulse response h of t when my system H has an input x of t, where x of t is equated to the Dirac delta function. In other words, h of t is equated to my system when the input is this delta function, delta t. All right, so now what we say is that since we're looking for the impulse response, the system must start at a 0 state history before the impulse strikes. So basically we're saying that imagine this x is this impulse. So 0 all the way until it shoots up here towards infinity, and then 0 after 0, where again this here is t. So as a result, we can confidently say then that V out of 0, or my initial condition, is equated to 0. So then using equation 2, which we saw on the previous slide, I can say then that V of t is equated to 0 e to the minus t over tau plus 1 over tau integral from 0 to t. Instead of vi of t, I'm going to replace it with this impulse function here, delta t. I hope this makes sense. E to the minus t minus lambda over tau d lambda. There should be a v out of t here. Since this is 0, this simply becomes 0. So then now we are left with v out of t is equated to 1 over tau integral from 0 to t delta lambda. I'm going to go ahead and pull out this e to the minus t over tau, e to the plus lambda over tau. Similar to the previous slide, remember this here is just a constant when talking about lambda. So then this is equated to 1 over tau e to the minus t over tau integral from 0 to t delta lambda e to the lambda over tau d lambda. We can go ahead and use the shifting property here, which says that this delta function kills the entire integral except for at lambda is equals to 0. And I have proven this property in a video called Continuous Time Fourier Transform of the unit impulse function, clearly explained. And I'll post that in the top right-hand side corner of this video. You can skip to minute number 230 to find this specific property proven. But essentially, this becomes the integral from 0 to t delta 0 e to the 0 over tau d lambda. This here is 1, and the integral from 0 to t delta 0 d lambda is equated to 1. So then this entire thing here simply goes to 1. Again, this is proven in the aforementioned video. So then therefore we could say that V out of t is simply equated to this 1 over tau e to the minus t over tau. And remember, this is for t greater or equals to 0, because for t less than 0, it's equated to 0. So what we can write as a one-line function is say that V out of t is equated to 1 over tau e to the minus t over tau ut. And again, this is equated to this h of t, or my impulse response, simply again because the input was this delta function, delta t. Let me go ahead and call this equation number 3. I want to explicitly state that this here is the RC circuit response to an impulse input, or you can say it is the impulse response of an RC circuit. I hope this slide makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Something we should note is that now we have two ways of solving for V out of t. We have this equation number 2, where if you remember, this here was my initial condition of my output, so V out at 0. And this here was my input, Vi of lambda. And the beauty of convolution, which we've seen here, is that now that we found this impulse response of this RC circuit, or this linear time invariant system, this low pass filter, we can now use this convolution equation, which I will call equation number 4. I hope the reason why we want to find this impulse response makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. All right, so now that we found this impulse response in our equation number 3, we can go ahead and solve for y of t is equated to x of t convolved with my impulse response, where remember, the problem says that x of t is equated to cosine of t u of t. And just to be explicit, h of t is equated to 1 over tau e to the minus t over tau ut. Now let's not forget that this x of t again is my voltage input of t, and this y of t here is my voltage output of t. And the reason why I keep bringing this up is because the whole point of this video is mapping signals and systems notation like x of t and y of t to circuit analysis notation like Vi of t and V out of t. Okay, from a previous video, we know that y of t is equated to this convolution computation is equated to the integral from negative infinity to infinity x of lambda h of t minus lambda d lambda. And again, the reason why we're using lambda is because tau is already taken by our time constant here. Something which I forgot to mention in the previous slides, which I will post as a text format in editing, is that tau is equated to RC, or my time constant is equated to RC, given that R is 1 ohm and my capacitance is also 1 farad. As a result, tau is just 1 second. So to continue with this equation, I can say that this is equated to the integral from negative infinity to infinity. X of lambda is going to be this cosine lambda u of lambda. H of t minus lambda is going to be 1 over tau e to the minus t minus lambda over tau u t minus lambda d lambda, where again, remember, tau is equated to 1. So let's go ahead and see what these two functions here and here are doing. So if I draw a graph where this is with respect to tau, we can see that this u of lambda is just the unit step function. So it's going to be 0 all the way until 0. And then it's going to shoot up to 1. And it stays at 1 all the way to infinity. So this is 1. This function here is u lambda. So the next function we want to see what it's doing is this ut minus lambda. And what I'll do is I'll reference the viewer to a video that I made in the past called Convolution Example Part 1, Clearly Explained, where I explain exactly what this function is doing in the 7th minute of that video. But essentially, if we consider t is greater than 0, that function is going to be 0 all the way until tau is equated to t, and then it's going to shoot up to 1, and then it's going to stay at 1 all the way to negative infinity. What we're going to notice is that this function and this function are being multiplied by one another. As a result, 0 here times 1 here is 0. So we don't care about what happens in this region. Same as this region here, because it's 0 times 1, which is just 0. So we only care about this region, 1 times 1. So now as a result, this u lambda and this ut minus lambda go away. But then we notice that our new equation, y of t, again, which is my voltage out of t, is equated to the integral from 0 to t. So the integral from 0 to t cosine lambda, 1 times 1, because tau is just 1, e to the minus t minus lambda over tau d lambda. So what I can do is separate my exponents. So this is equated to the integral from 0 to t cosine lambda times e to the minus t over tau times e to the lambda over tau d lambda. And again, we know that tau is just 1 here and 1 here. So we can get rid of this since it's just 1. And then this is equated to this e to the minus t is a constant when talking about lambda. As a result, I can pull it out. So then this becomes e to the minus t integral from 0 to t cosine lambda e to the lambda d lambda. All right, so now we have to do some heavy maths to solve this integral. So what I can say now is that this is equated to e to the minus t integral from 0 to t e to the I lambda plus e to the minus I lambda over 2. And what I'm using here is something called the inverse Euler formula of a cosine function. Obviously here, this is times e to the lambda. This is d lambda. So this is equated to, let me pull out that 2. I'm left with e to the minus t over 2. Integral from 0 to t e to the I lambda plus lambda. What I'm basically doing is distributing this lambda to this term and this term. So then I get plus e to the minus I lambda plus lambda d lambda. All right, let's keep going. This is equated to e to the minus t over 2. Integral from 0 to t. Let me pull out a lambda. So e to the lambda I plus 1 plus e to the lambda minus I plus 1 d lambda. And now let me solve for the integral. So this is equated to e to the minus t over 2 times e to the lambda I plus 1 over I plus 1 plus e to the lambda minus I plus 1 over minus I plus 1. And then this is evaluated between 0 and t. Evaluating this gets us e to the minus t over 2 times e t to the I plus 1 over I plus 1 minus e to the 0 over I plus 1 plus e t minus I plus 1 over minus I plus 1 minus e to the 0 over minus I plus 1. Obviously, e to the 0 here is 1, and this here is also 1. And what I'm going to do now is I want a common denominator of I plus 1 and minus I plus 1. So as you can imagine, this is going to be equated to e to the minus t over 2 times this term here is missing a minus I plus 1. So minus I plus 1 times e t I plus 1 minus, this one is missing a minus I plus 1 plus this one is missing an I plus 1. So then it's I plus 1 e t minus I plus 1. And then last but not least, minus I plus 1, because that's what it's missing. And then you could put this all over I plus 1 times minus I plus 1. Feel free to go ahead and pause the video and make sure this makes sense to you. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Let me go ahead and scroll down a bit to give myself some more room. And what we want to notice is how long this is taking for a given input. It's very important to see how long this convolution method is taking for a input cosine of t u of t. All right, so let's go ahead and continue. So then this is equated to e to the minus t over 2. Let me go ahead and separate this term and this term. So then this is times minus I plus 1 e to the it times et plus I minus 1 plus I plus 1 e minus it times et minus I minus 1. And again, this is all over. Let me go ahead and distribute this here using the FOIL method. So I times minus I is simply 1. I times 1, this is going to be plus I minus I plus 1. And this is here closed up. As you can see, this cancels out. And this here is equated to 2. So let me go ahead and erase the entire thing and simply write in 2. Another thing we notice is that this I cancels out with this I here. So as a result, I'm going to erase them. So then this here is minus 1 and this here is minus 1. Minus 1 is minus 2. So I'm going to write a plus here and a minus 2. If I go ahead and continue, what I'm going to do is I'm going to pull out this et from this function and this function. And in order to do that to this function, it's going to remain an e minus t. All right, so what I'm going to do is this is equated to e to the minus t times et over 2. So then this is multiplied by minus I plus 1 e to the it plus I plus 1 e to the minus it, because I pulled those et's out. And then in order to do that to this term, it has to be minus 2 times e to the minus t. And then this is all over this 2. Again, if you're confused by this step, simply distribute this e to the t to all three of these functions and realize that you get this function here. And the trick behind doing this is now we can cancel this function and this function. So then now we can say that y of t is equated to 1/2. If I go ahead and distribute e to the it to this value here and here, what I'm left with is times minus I e to the it plus e to the it plus I e to the minus it plus e to the minus it minus 2e to the minus t. This is all over 2. Let me go ahead and say that this here is a term I call term 1. This here is a term I call term 2. This here is a term I call term 3. This here is a term I call term 4. And this here is a term I call term 5. So then y of t is equated to this 1/2 times, from terms 1 and terms 3, I'm going to pull out a negative I value. So then term 1 just becomes e to the it, and terms 3 just becomes minus e to the minus it. Let me go ahead and now write terms 2, 4, and 5. So this is plus e to the it plus e to the minus it. And terms 5 is minus 2e to the minus t. So then what I'm going to do now is this 2, I'm going to say over 2 here. I'm going to say over 2 here, and I'm going to say over 2 here. Since it's a common denominator, I can do this, and I hope this makes sense. If you have minus I in the numerator and you want to bring it to the denominator, it just becomes a positive. So I can cancel this I, and I can write it down here. And finally, we can see that this here, using Euler's formula, is cosine of t. And this here is sine of t. And obviously, this 2 goes away with this one here. So let me go ahead and write y of t out neatly. So y of t is equated to this 1/2. Don't forget about it. So this is 1/2 cosine of t plus 1/2 sine of t minus e to the minus t. And remember, since we said that x of t, which is equated to our voltage input of t, is this causal system, or basically it's equated to 0 for t less than 0. And we said it was cosine of t for t greater or equals to 0. This combines by saying x of t is equated to cosine t u of t, right? This unit step function. We also say that our output, y of t, has to be multiplied by u of t, right? Because it's going to be 0 for t less than 0. All right, so I want to draw a couple conclusions. The first conclusion I want to draw is that this here is what's called the steady state response, right? And steady state is basically as my system goes all the way to infinity, how does my system respond, right? It steadies out in this 1/2 cosine t plus 1/2 sine t, where this here is what's called my transient response. And essentially the transient response is how your system behaves on that initial impulse. So my input x of t was this unit step function, right? So it went like this, and then it started having a little cosine function to it, right? So this initial impulse here of my x of t, how does my output respond to it? This value e to the minus t tells us how it responds to that initial transient. Something that I'll encourage the viewers to do, which I won't do in this video, is go ahead and graph this v out of t is equated to y of t in Desmos, and see what you're getting for the transient and the steady state response, and visualize it for yourself. And the last conclusion I want to draw on this slide is that now we have 2 ways of finding this v out of t, which is also equated to y of t, given any x of t, right? The first way is using this equation number 2, which we showed earlier in one of the slides. And the second way is using equation number 4, which again was this convolution operator, which we've shown right here. And what again I want to stress is realize how tedious this method was. All right, so now let's go ahead and do goal number 3, and then finally draw some conclusions in goal number 4. Okay, for goal number 3, we said that we can find this y of t, or this voltage output, by taking the sum n of h of Sn, an of e to the Sn t, where some textbooks might call this x of nt. And essentially x of nt is your input decomposed into complex exponentials. And again, I've made a video on this in the past called Convolution to Multiplication Example Part 2 Clearly Explained, which I'll post in the top right hand side corner of this video. We've talked about this before, but this h of Sn is my transfer function. All right, in order to find this h of Sn, we say that h of Sn is equated to the integral from negative infinity to infinity h of lambda e to the minus Sn lambda d lambda. So then this is equated to the integral from negative infinity to infinity. H of lambda is just my impulse response. So 1 over tau e to the minus lambda over tau u lambda times e to the minus Sn lambda d lambda. Again, remember tau in this case is equated to 1. As we already know, this unit step function restricts my integral. So this is equated to the integral from 0 to infinity of 1 over 1 e to the minus lambda over 1, which I won't write, times e to the minus Sn lambda d lambda. So then now this is equated to the integral from 0 to infinity e to the minus lambda 1 plus Sn d lambda. So now the integral of this function is equated to e to the minus lambda 1 plus Sn over 1 plus Sn from 0 to infinity. If I go ahead and plug this in, I get that this is equated to E0 over 1 plus Sn minus e to the minus infinity over 1 plus Sn. As you can see, e to the 0 is 1 and e to the minus infinity is 0. So we're left with our transfer function h of Sn is equated to 1 over 1 plus Sn. Again, something to note is that this Sn is some complex frequency variable. And we've talked about this Sn in the past. Now, to continue solving y of t, we need to acknowledge one thing about my input xn of t, where we say that x of t is equated to this cosine t u of t. And this function looks something like this, which we've drawn in the past. It's 0 all the way unto 0. Then my cosine starts like that. As a result, this function here is not perpetual. That means that it has not been existing or running smoothly for an infinite amount of time from t is equals to negative infinity to t is equals to positive infinity without starting or stopping points. Right? Again, this function here is not perpetual in existence. We can also say that this function is not continuous in existence. And to be continuous means that there is no turn-on moments or sudden breaks in my function. As a result, since one of my criteria for using this eigenfunction equation was that my system has to be continuous, again, check out the video called Eigenfunctions of Continuous Time LTI Systems Clearly Explained, I therefore technically cannot use this equation. But let's go ahead and modify x of t so that I can use this equation. And in order to do so, I can say that x of t is just simply equated to cosine of t, where if I wanted to draw cosine of t here, I'm left with something that looks like this from negative infinity to infinity. And now since this function here is a continuous system or a perpetual system, I can go ahead and use this equation. Now, in order to break down x of t into the addition of these complex exponentials, I can do a couple of things. The first thing I can do is apply the inverse Euler's identity of a cosine function. So essentially, x of t is equated to e to the it plus e to the minus it over 2, which again, I can say that this is e to the it over 2 plus e to the minus it over 2, where here we get x1 of t plus x2 of t. Again, something we should note, because this video is meant to bridge circuit analysis to signals and systems, is that if we want to use the Fourier series to write cosine t in terms of these complex exponentials, we can do so. As well as if we wanted to use the continuous time Fourier transform to write this cosine t in the sum of complex exponentials, we can also do that as well. Again, I have made videos about these two topics in the past, and I'll post them on the top right hand side corner of this video. So please feel free to check that out. So now what we can say is that x1t and x2t is written in this format here, right? Where in this case, a1 is equals to 1/2, s1 is simply equals to I, a2 is equals to 1/2, and s2 is simply equals to minus I. Let me go ahead and write the summation now for y of t. So y of t is equated to h s1 times x1 of t plus h s2 times x2 of t. So then this is equated to h times I, which is s1, times x1 of t plus h times negative I times x2 of t. So then we get hi is 1 over 1 plus I. x1 of t is simply e to the it over 2 plus h of minus I is this 1 over 1 plus negative I. h2 of t is e to the negative it over 2. What I can go ahead and do is find a common denominator between these two terms. This essentially is 1 minus I times e to the it plus 1 plus I e to the minus it over 2 times 1 plus I times 1 minus I. We found that from a previous slide, this here is equated to 2. So then if I rewrite this and distribute e to the it to this terms here and e to the minus it to this terms here, I get e it minus I e it plus e to the minus it plus I e to the minus it over, let me just say 2 times 2 for now. I wanted to try and put this on one slide, but I'm going to have to scroll. But what I'm going to do is I'm going to leave the graphs for the x is equals to cosine on the page. What you're going to notice is that we're going to get a y of t is equated to 1/2 times, let me write this term plus this term here first. So this is e it plus e to the minus it over 2 plus, if I go ahead and pull out a minus I from this term and a minus I from this term, I'm left with minus I e to the it minus e to the minus it, parentheses here and here, over 2. So then similar to our previous slide, we know that to move this to the denominator, we just simply make it a plus. So we can get rid of it here. And then it becomes a plus I in the denominator. So as you can see now, this here is that cosine of t, and this here is that sine of t. So then again, this is equated to 1/2 cosine of t plus 1/2 sine of t. As you can see, in this solution, we only get our steady state response and not that transient state, right? Which was this minus e to the minus t over 2. So, right, we do not get this. Okay, there's a reason for this, but let me go ahead and clean this up and say that there's a times u of t here. And again, this is my v out of t, or again, this y of t. And now the reason why we don't see a transient is because this function x of t that we adapted here is continuous, right? There is no stoppage or breaks in the function. So my output is not going to have some type of transient result. Again, we say that because we had to modify our input from x of t is equated to cosine u of t to satisfy the Eigenfunction Theorem. Since we had to modify it to this, as a result, there is no transient in this output y of t. But nonetheless, the take home point here is, as you can see, given an input x of t, the work that is done here, right, finding this transfer function of my system and simply multiplying it by each of the decomposed complex exponential of my input and then adding those up together is way easier than doing y of t is equals to my input convolved, or the convolution operator, times my impulse response h of t. This here has been the driving point of this entire video. Okay, so now if we go ahead and do the goal number 4, which is to draw some conclusions about this video, we can summarize the methods which we use to solve for my output v out of t in 4 different ways. The first one is located here, which is what I'll call a circuit analysis method, or CAM for short. So then let me go ahead and write CAM here. The second method is located here, which is our equation number 4. So the second method is what we consider the convolution. So y of t is equated to my input x of t convolved with h of t, my impulse response. And then the third version is located here. So the third version is what we call the Eigenfunction Theorem. And I'll say the fourth method after I talk about the pros and cons of all these methods. So what I want to do is go ahead and categorize these things in terms of computation, and then I'm going to have a column called transient and another column called steady state. Okay, for the circuit analysis method, as you can see, this equation number 2 is pretty hard to do. Let me consider this as hard and say that this is integrals, right? Because you're taking an integral here, right, which can be cumbersome. The good thing about this method, though, is that when you put in any input, vi of lambda, into my system, I'm going to get my transient and my steady state. The same thing we could say with convolution is that it is hard to do in terms of computation, right? Again, you're dealing with integrals, but the pro is that you do get transients and steady states. For this Eigenfunction theorem, it's a bit easy, right? We say that it is easy because you're dealing with multiplication and addition. But unfortunately, if your input is perpetual or continuous, you do not get the transient like we saw in the previous slide, but you do get the steady state. So now we have to ask ourselves, is there a method that allows us to get best of both worlds, where we get a computation that is easy, so multiplication addition, and we get both the transient and the steady state response? And that method is what's called the Laplace Transform. Now, a lot of students know about the Laplace transforms, but they don't know or understand how powerful it is. So I hope this video kind of breaks down and shows you exactly why we need the Laplace transform. Specifically, the computation is easy using things like multiplication and division versus integrals, and we get my transient and my steady state response in my solution. Now, the next video I'm going to make is going to be a video on Laplace transform, so please look out for that. And since this video is pretty long, I don't want to dive too much into what the Laplace transform is, but just understand that we need it because it allows our computation to be easy, and it gives us my output's transient and steady state response given an input. If you have any questions or concerns about this video, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge given in the video. If you like the content the YouTube channel is providing, please consider subscribing to the channel because it really helps the algorithm. And lastly, if you want to support the channel, you can also check out my website at professorgovala.com, where I have different apparels and different accessories which you can purchase for sale, where the profits made from the sales are directly invested back into the channel to help grow the channel. Thank you.